All right, so right, as threatened last time, you have to remember what happened last time to understand this time. But just in case you don't quite remember, a brief summary. So what happened last time is I defined the amplituhedron. To define it, I first needed to define this amplituhedron map, which required picking an auxiliary matrix Z of a certain size. And all that map was, right, so this took the totally non-negative Grassmannian into another Grassmannian. Here, sorry, let me write actually even more stuff. Right, so we had this Z tilde map. It mapped TNN GRKN into GRK K plus M, and this was just the map induced by matrix multiplication. So nothing too crazy, right? If I had my subspace represented by matrix A here, it gets mapped to the subspace represented by matrix A times Z here. And I had some positivity constraints on Z. I wasn't picking a random matrix Z, I was picking one with positive maximal minors. Okay, so that gave me the amplituhedron map, and then the amplituhedron is just the image of the TNN Grassmannian under this Z tilde map. It is sitting in this ambient Grassmannian, GRK K plus M, and it's full dimensional there, so it's K times M dimensional. And motivated by this question from physics of interpreting these BCFW formulas, we're asking a particular question about the amplituhedron. So there's many questions to ask, but the ones we're going to pay attention to, we're going to focus on some specific pieces of the amplituhedron. So these pieces are, we're calling them tiles, and they're images of positroid cell closures, but only special ones. Like, we don't care about arbitrary positroid cell images. We care particularly about those where the Z tilde map is injective on the positroid cell, and the piece downstairs, so equivalently the piece upstairs, is full dimensional, it's K times M dimensional. Okay, so those were our tiles. And what we were interested in are tilings of the amplituhedron, which are decompositions of the amplituhedron into tiles that have pairwise disjoint interiors. So they cover the whole thing, and they only overlap on their boundaries. Okay, and the question we're going to talk about today is some combinatorics of the tiles and tilings for M equals 1 and 2. And then tomorrow we'll do techniques for higher M, so M bigger than 2. What did I want to say? Oh, right. Before I move on, like last time, I gave this long list of questions about the amplituhedron and some partial results, and I terribly misquoted a paper, and Balazs caught me. So let me write let me write the correct result. So this was the Ranestad Intellin result, which is all of the amplituhedra that sit inside of GR24 are positive geometries. So last time I replaced this n by a particular number, which made this result actually fairly trivial, but no, it's actually an n, so they prove some infinite family of amplituhedra are positive geometries. Okay, I'm not going to say anything more about this, but it was such an egregious error I had to say out loud what the correct thing was. Okay, so that said, all right, so last time, right, I told you all about the amplituhedron and these tiles and tilings, and I gave you this really long list of open questions, and so you might feel like, okay, maybe I myself would like to think about some of these questions. So the first thing I want to do, actually, before talking about small m, is some useful tools to study amplituhedra. And the tiles. Okay, and the first of these is, okay, so the amplituhedron is sitting inside of GRK K plus M. So one way to try to describe the amplituhedron or these tiles is using the Plücker coordinates of GRK K plus M. Right? That would be like kind of a reasonable thing to do. It turns out that this is much messier than using some other functions to describe the amplituhedron. And so I want to introduce you to these other functions before we do anything else. So the right functions to use to study tiles are, well, they're not the Plücker coordinates of the ambient Grassmannian. Instead, not the Plücker coordinates of GRK k plus m. Instead, there are these other functions, which I will define for you right now. Okay, so these other functions, they're called twistor coordinates. I think for physicists, these in some sense really are momentum twistors. Okay, but to define these, what do I need? I need to pick m numbers between 1 and n. Okay, and these are going to be functions on my ambient Grassmannian of GRK k plus m. Let me pick some point x in there. Okay, and then these are sort of the right functions for the amplituhedron, so I'm also going to have in the back of my mind my auxiliary matrix Z, like the one I fixed for the amplituhedron. Okay, and if I pick all of these things, then I can define the twistor coordinate. Which I'm going to denote by bracket I1 through IM, and then the point x where I'm evaluating this twistor coordinate is going to be a subscript. Okay, and how is this function defined? Well, I'm going to take a determinant of a matrix. This matrix has x in the top, and then, okay, so this is k rows and k plus 1 columns, so I need to pick m more vectors to put here to get a square matrix. And the m vectors I'm going to pick are the I1th through imth rows of Z. Okay, so this matrix Z, sorry, bad board work, it's got rows Z1 through Zn, and I'm just going to take row Zi1 and put it here, and then row Zim and put it there. Now I have a square matrix, and I can just take this determinant. Okay, so why are these the right functions? Well, okay, I guess they're the right functions because you'll see we'll be able to do a lot with them. But one reason you can already tell they're maybe better than the Plücker coordinates is that they know something about this matrix Z. So, like we talked yesterday, there's conjectures that none of the important properties of the amplituhedron depend on Z, but definitely like which subset of GRK k plus m it is depends on Z. Yeah. Yes, thank you. That's right. So these, this is just some linear function in the Plücker coordinate, in the Plücker coordinates of x. So the coefficients, I mean, you can just expand this determinant using like Laplace expansion with this being one of your blocks, and you'll get this expands as a linear combination of these pi's where the coefficients are certain minors of the Z matrix. But they're not maximal minors, so we sort of don't know that much about it. Yeah, so this is not too crazy, right? I'm just sort of, yeah, I'm thinking about, instead of the standard coordinates, I'm just taking some linear transformation of them. I'm thinking about those instead. Okay, right, so just to immediately display for you the usefulness of these equations, of these functions, yeah, so I'll just say these functions are very useful for inverting the Z tilde map. So if we're in the situation where we have a tile, we know that the Z tilde map is invertible, and so you want to give some formulas for the inverse map. And these functions are good for that sort of thing. So here's an example. So let's do k equals 1, m equals 2 example. So this is the situation where the amplituhedron is just a polygon. And we talked about what the tiles were. The tiles were just triangles inside of the polygon. So maybe this is, yeah, so this triangle is one of the tiles. Okay, so, right, so let me actually write down. So how do I get a point in this tile? Well, I take a matrix that looks like ABC and then a bunch of zeros, right? And I map it to AZ1 plus BZ2 plus CZ3. And now, okay, so this gives me some point down here. And okay, this is my point X living inside of GRK, K plus M, which in this situation is GR1, 3. And now I want to recover this matrix A from X. So I want to write down some functions of X which are equal to A, and then another function that's equal to B, and another one that's equal to C, right? That's how I invert this map. So how do I write A, B, and C in terms of the matrix X? Well, one thing that I could do is I could compute, for example, the twistor coordinate 2, 3 of X. Okay, so what is this? Well, I'm supposed to put X in the top. AZ1 plus BZ2 plus CZ3. And then I'm supposed to put the second row of Z and then the third row of Z. And the determinant is linear, right? So having this Z2 here means that we can kind of cross this out, right, without affecting the value of the determinant. And also this Z3 means we can cross this out and it won't affect the value of the determinant. So, sorry, I'm supposed to be taking a determinant. So this twistor coordinate is the same thing as the determinant of AZ1, Z2, Z3, which is the same thing as A times a Fluker coordinate of the Z matrix. Okay, so I just showed you using the twistor, like the twistor coordinate of X is almost this thing A that we're interested in. It's this thing A times a maximal minor of the Z matrix. Okay, so I can do the exact same thing, the exact same computation, but instead of 2, 3, maybe if I pick 1, 3, X, if I do this, what I get is minus B times P 1, 2, 3, X. I hope that's believable. So now I would just get a B, yeah, so I don't know. I hope this is believable. Maybe I'll leave it at that. Okay, and then if I compute, sorry, Z, yes, there we go. No wonder people look confused. Okay, and then if I compute the twistor coordinate 1, 2 of X, I get C times P 1, 2, 3 of Z. So what I see is, okay, if I look at this, let me look at the point in projective space whose coordinates are the twistor coordinate 2, 3x, then the twistor coordinate minus the twistor coordinate 1, 3x, then the twistor coordinate 1, 2x, and then a bunch of zeros. As a point in projective space, this is the same point as my original point A, right? Because, well, this is A times something, this is B times that same thing, and this is C times that same thing again. So using the scaling, I can get rid of that extra factor, and I've recovered A. So this is supposed to convince you, like, these are the right functions to use to describe these inverse maps, because, like, for this particular tile, this is the inverse map. You send X to this point in Pn, and that's the inverse of the Z total map. Okay, so cool. Yeah, so we're going to keep using these twistor coordinates as the functions to use to invert the Z tilde map. I think if you're a physicist, maybe you're just happy to have something called twistor coordinates in view. Like, this seems good. For m equals 4, they have 4 indices, and that also probably seems good. If you're a mathematician, maybe you feel a little bit like, well, where did these functions come from? I mean, do you just pull them out of somewhere? So there's a more conceptual way of thinking about these twistor coordinates, which I expect, well, maybe it will be useful for someone, so I will say it. So, okay, so more conceptually, where these coordinates come from is we have what I'll call the twistor embedding which is a way to take grk plus m and stick it inside of the Grassmannian grmn. Okay, and the way that this embedding works is it depends on the matrix Z that I chose. So it's not canonical, it depends on the Z I picked. Okay, I'll write down the formula. So what does it do? Okay, this is not probably illuminating. What does it do? It takes my point x and grk plus m, and it maps it to, what I do is I take a matrix representing the orthogonal complementary subspace, and then I multiply by Z transpose. So, all right, I'm asserting for you this is an injection, and it actually lands, okay, this Grassmannian is much smaller dimensional than this one. So the image of this twister embedding is something relatively special. So it's the Grassmannian, so the image of this twister embedding is the set of M planes in R to the n that are also contained in the column span of the Z matrix. Okay, so I'll write this first. So this W here is the column span. This might look pretty weird. Okay, let me say some things. So what's happening, so if I just think about this, those M planes which sit inside of the column span of Z, this is a linear slice of this very big Grassmannian grmn. Because one subspace, like one subspace sitting inside of a fixed other subspace, this is a linear condition in the Plücker coordinates of one subspace. Okay, so what I'm doing is I'm taking grk plus m, and I'm sticking it inside of a linear slice, relatively small dimensional, of grmn. Okay, what's the advantage of doing this? Well, if I do this, I can kind of think about all z's at once. Like in here, inside of this grmn, I've got this grmw for any z. So they all are kind of living together. That's maybe one advantage of doing this. Okay, yes? Yes, because like Z is telling me which linear slice of grmn I live in. So if I change which Z I'm doing, I'll like actually end in a different subset of grmn. Yes, yes. You will like if yeah, I mean if the two matrices Z have different column spans, then you'll just land, like the image will live in maybe, yeah, they'll just live in two different linear slices of grmn. That's right. The result depends on the column span of Z, but I think maybe not on anything else. I'm not sure, but it definitely depends on the column span. Okay, more questions. Yeah, so sorry, so I wrote this, I should do this. So this embedding has image this grmw. So what I'm doing, yeah, and so it's a homeomorphism onto this part, and it sits in this bigger Grassmannian grmn. You cannot, I don't think you can apply z tilde here. Yeah, or if you are, you've like swapped, you've exchanged the roles of m and k, and that's kind of a dramatic thing to do. Yeah, so I don't know what happens if you apply a z tilde map to this space. Yeah, okay. So, right, I said, okay, so what did I start with? I started with these twister coordinates, and then I switched to this twister embedding. So how were they related? Oh, yeah, but this was like, this would send this picture into some gr2n. And then I don't know, yeah, you shouldn't like apply the z tilde map after you're in gr2. Yeah. Okay, so why did I start talking about this? It was supposed to give a conceptual understanding of where these twister coordinates come from. So what are the twistor coordinates, now that we know this twistor embedding? Well, one can work out that, sorry, I'm going to get the directions wrong. One can work out that the twistor coordinate I1 through IM, this is the pullback of the Plücker coordinate PI1 through IM by this twistor embedding. So what you should think about it is you have natural coordinates here. They're the Plücker coordinates. And then you can think about what they mean if you decide to view your point as a point in GRK K plus M instead of as a point in GRMN. And the twistor coordinates are what you get when you decide to do that. So the twistor coordinates are sort of very natural coordinates somewhere. It's just inside of this larger Grassmannian. And I've just kind of imported them backwards using this twistor embedding map. Okay? Yeah, and I think for physicists that is not a good way to think about twistor coordinates, but for me it is a good way to think about twistor coordinates. Okay, and then yeah, let me say one more thing since I have gone through the trouble of telling you this map. So sometimes it's useful to think about this composed map where first I do z tilde and then I do this twistor embedding. Right? So that means I'm taking the amplituhedron which lives here and I'm just transporting it without disturbing it, right? Transporting it homeomorphically into this GRMN. Okay, I'm going to give this map a name. This is z double tilde. Okay, and why is it sometimes useful to think about this? So if you have some point in totally non-negative Grassmannian, so in the domain of the amplituhedron map, and you have some other point living in the image of this twistor embedding, so y is in GRMW, then it's not too hard to figure out if y is the image of A under this z double tilde. So z double tilde of A is equal to y if and only if y is perpendicular to A. Okay, so y being perpendicular to A, I mean, you can phrase this as y is in the orthogonal complement of A, or if you're thinking of matrices, if you dot something from here with something from here, you get a 0. Okay, and why is this any better than thinking about like the z tilde map? Well, things being orthogonal, that's like something being equal to 0. This is maybe an easier thing to think about or to check, versus with the normal z tilde map, we would want to say, well, you know, my point x, like with the normal z tilde map, we've got like z tilde of A is equal to x if x is equal to A times z, which this is a perfectly reasonable equation. It's just a little bit harder to think about than two things being perpendicular. So that's the reason why sometimes it's a little easier to think about this composed. Okay. Any questions? Things are about to get much more concrete. This was sort of the general nonsense, some tools to think about the amplituhedron. Okay, now things will get really concrete, and we will just talk about, in examples, what happens. So, okay, here's some very concrete information about m equals 1. And again, this is from this work of Karpin-Williams. Right, so there are not that many papers about the m equals 1 amplituhedron because Karpin-Williams sort of answered a lot of the questions. Yeah, so they kind of give a very complete understanding. Okay, so what did I say we cared about? We care about these tilings. And right, for m equals 1, I already told you the amplituhedron itself is a very nice bounded complex of a hyperplane arrangement. And I even already told you what the tiles were, but now that we have a bit more kind of language, let me give you a bit more information. So the amplituhedron itself is this stuff in pink. Okay. And one thing we said, okay, right, so we know and K1Z is a bounded complex of a hyperplane arrangement. Okay, and now I can tell you what are the hyperplanes actually. So the hyperplanes are just, okay, so here we're in m equals 1. So for a twistor coordinate, I just pick one index. And my hyperplanes are exactly the ones given by some twistor coordinate is equal to 0. Okay, so in this hyperplane arrangement, I'll always have exactly n hyperplanes. Okay, and this hyperplane up here is when the twistor coordinate 1 is equal to 0. This one is the twistor coordinate 2. This is the twistor coordinate 3. This is the twistor coordinate 4. Okay, and I'll also tell you the normal vector that I'm choosing is this one. So yeah, this is the this is the region of the plane that's in the positive side of all of the hyperplanes. Okay, so that's nice. It's very easy with our good choice of functions to describe the hyperplanes. Yeah, okay, I didn't write this down. Do I want to tell you? Yeah. Okay, maybe I'll say it this way. So we also talked about, right, so we also know a tiling. So each region of the hyperplane arrangement, so like this quadrilateral, that's a tile. And it's actually easy to give indexing sets for these smallest tiles. So theorem is the regions of the hyperplane arrangement, the bounded regions, sorry, are tiles, and they're indexed by, so you get to, there's a couple of different indexing sets. So one indexing set is I can just look at I can just record which side of each hyperplane this region is on, right? So this region is associated to a sign vector. That sign vector just records, okay, well, I'm on the plus side of the one hyperplane. I'm on the minus side of the 2 hyperplane. I'm also on the minus side of the 3 hyperplane, and I'm on the plus side of the 4 hyperplane. Okay, so these bounded regions, which are tiles, they're indexed by sign vectors of exactly this sort, with, I don't get this wrong, with exactly k sign flips. Right, so this vector, plus, minus, minus, plus, I see 2 sign flips. Here I go from plus to minus, and then here I go from minus to plus. And maybe another thing that I'll say is, well, no, okay. There's also a different indexing set. Like maybe you want, okay, so, okay, this description, sign vectors with k sign flips, this is describing for you the tile downstairs. It's actually giving you like a semi-algebraic description, right? Because that sign vector is telling you, okay, well, this is the region where the first twistor coordinate is positive, and the second one is negative, and the third one is negative, and the fourth one is positive, right? So this sign vectors with k sign flips thing, this also gives you a semi-algebraic description of the tile. Okay, but maybe you don't want a semi-algebraic description of the, oh yeah, you have a question? Yeah, that's right. That's right. yeah, it's sort of, it really comes from, yeah, like the Z matrix is telling you what these twistor coordinates are, and you have like a preferred choice of, yeah, of which normal vector. It's in their paper. I don't quite remember. Okay, but maybe you would like to know instead, like, which cells of the TNN Grassmannian are these tiles images of, right? So like, which cells upstairs are those ones that are mapped injectively down? So this is also very easy to say. So if you want the cells, or like the playbit graphs for the cells, what you do instead is you index by partitions of 1 through n into subintervals, disjoint subintervals. Okay, and in particular, you want to use n minus k disjoint subintervals. Okay, so, and they should be non-empty. Okay, and from this indexing set, I'll be able to read off the playbit graph of the cell that maps down. Okay, oh, what else should I say, actually? These two things are related. So if you have a sign vector with k sign flips, it's a sign vector of length n. So if you draw a bar every time the signs stay the same, then you get one of these partitions. So that's how to go between these two indexes. Doesn't really matter. Maybe you should just take as given. So I could alternately index the tiles by this thing. So here's an example. Okay, so maybe I pick this partition of 1 through n. Okay, so this is a partition of 8 into 4, which is n minus k subintervals. So that means that k is equal to 4 here. Okay, so this indexes one of my tiles downstairs. And this tile comes from, like, is the projection of the following positroid cell. So what I do, okay, so I draw 1 through n on a line going backwards. Okay, and all I do is for each part in my partition, so for like 1, 3, I'm going to draw a little spider, which is a black vertex kind of connected to 1 and 2, but since I want to be bipartite, I have to add these degree 2 white vertices. Okay, and then I also, so I do the same thing for each part. So 3, 4, 5 is a part. So I'm going to draw kind of a spider with legs 3, 4, 5. And then 6, 7 is a part. Spider with legs 6, 7. And then any singletons, I actually just leave them alone. Like I just get a vertex, I don't attach it. Okay, so if you want to know what cell this particular tile came from, it came from the cell indexed by this playbit graph. So you have kind of like complete information. Everything you want to know about m equals 1, you can write in a really explicit combinatorial. So each time there is not a bar, the sign, oh God. Yeah, so sorry, okay. I said it out loud before, I just have to remember what I said. So I want k sign flips. Okay, well, n minus k and k are equal. I think where the signs stay the same, that's where the bars are. So this is plus, that's minus, plus. Why did I start with plus? Oh, projective, this is all, it's projective sign vectors. Yeah, sorry. So I could have started with a minus, but that should describe the same region because everything is projective. Elijah's just keeping me very honest for these lectures. I'm glad he's here. Okay. Right. Oh, okay. And then I got ahead of myself. So you can just read from all of this information the semi-algebraic description, and so I'll just write down what it is. So maybe I've chosen to pay attention to these graphs instead of one of the other representations. Then what is the corresponding tile? Well, it's going to be all of those points x in GR k plus 1, where the twistor coordinate I has sign -1 to the n minus I plus number of components of the graph in the interval I plus 1 to n. Okay, so this is an annoying exponent. The point is, whatever one of these combinatorial objects I pick, I can use it to write down the semi-algebraic description of the corresponding tile. Okay, and it's going to be, there's some combinatorial statistic in the exponent, but whatever it is, it's very concrete. Okay. Let's see. So this was for the bounded regions of this hyperplane arrangement, which I told you last time are the smallest tiles. And you can actually take unions of certain regions and still get tiles. Those are also characterized. It's just more annoying to state, so I think I won't bother, but it's a very similar kind of combinatorial description as this. So this is supposed to convince you m equals 1 is sort of, you can just work things out completely explicitly, lots of flexibility. Yeah, so any questions about m equals 1, then we'll go to the slightly more complicated situation. Right. Even if we don't care about combinatorics, we're at least satisfied that the combinatorics exists for m equals 1. Okay, yeah, and maybe I'll say again what I said last time, which is, like, as this picture says, the m equals 1 situation is like a linear situation. The Grassmannians, at least the domain Grassmannian, this GRK k plus 1, is just projective space. It's not interesting and curvy, and that's one of the reasons why things are so simple. So for m equals 2, we will see more complicated stuff, but still not that bad, actually. Okay, so. Okay, so there are more work on m equals 2 because it's more complicated. So the first people who constructed a tiling were Bao and He. So they gave a recursive construction for tilings of the m equals 2 amplituhedron. Then Lukowski, Parisi, and Williams connected the problem of tiling the m equals 2 amplituhedron with the tropical Grassmannian, in particular the positive tropical Grassmannian. They made some conjectures about this, also proved some results. And then myself, together with Matteo Parisi and Lauren Williams, we proved some of their conjectures and gave a complete description of the tiles and tiling. So this is what I'll talk about today. Okay, so unlike m equals 1, I can't draw you pictures of the actual tiles, but I can tell you exactly what the tiles are, both as semi-algebraic sets and like which cells they came from. So I'll start with a semi-algebraic, I will start with a good indexing set, a good combinatorial indexing set for the tiles, and then I'll tell you how to get all the other information from that. Okay, so tiles for NK2, whoops. These tiles, they're in bijection with bicolored subdivisions of an n-gon with area K. Okay, so this indexing set, this is supposed to be somehow the analog of either these signed vectors or these partitions of the interval. Okay, what is this? Let me show you an example. So I have my n-gons, let's say n equals 8. Okay, so a subdivision of an n-gon is some choice of non-crossing diagonals, which breaks it up into smaller polygons. That you probably know. So maybe I will pick this subdivision. This bicolored business means that I'm going to color my subpolygons hollow or solid. So maybe these ones will be the solid ones. And it has to be a proper bicoloring. So if two smaller polygons share an edge, they have to have opposite colors. Okay, and then what is this area statistic? So for the area is tracking, sorry, I just realized that this is a very bad octagon. Okay, I think this is flat. The area statistic is tracking how much of the polygon is black or is filled in. And so what I do is I triangulate the black polygons however I want, and I count the number of black triangles I see. Okay, so here, for example, I could triangulate this one like that, and altogether I see 3 black triangles, so this is an area 3 example. Okay, so let's call this picture sigma. And if someone hands you such a picture, you can produce for them a tile of the amplituhedron. And what I'm going to do is I'm going to tell you which playback graph to use. So I'm going to tell you the playback graph of the cell upstairs, which projects down to this tile. Okay? And then I'll give you a more direct description in a second. So what does this correspond to? So basically, I'm just going to, kind of very similar to up there, where I took my partition into intervals and sort of drew a playback graph on top of it. I'm going to take my bicolored subdivision and draw a playback graph on top of it according to some rule. So, okay, so the boundary circle for my playback graph is this, oh, sorry, I need to have numbers. Okay, so to draw the playback graph, I take my subdivision. I again triangulate the black polygons in some way. So maybe I choose this one. And then inside of each black triangle, I'm going to put a little tripod. So the tripod has a white vertex, and then its legs are exactly the boundary vertices of the triangle. So in pink over here, so ignoring all the white stuff, in pink is the graph G. And the assertion is that this is a graph for a tile. So if I take the corresponding positroid cell and map it down, the map is injective and also everything's the right dimension. Okay, so there's no reason for you to believe me at this point. I do want to talk actually a little bit about why this is true, because it's supposed to convince you that all of this general stuff I said before is actually useful. So let's think a little bit about why z tilde is injective on this particular positroid cell. So, sorry, so maybe I should call this G sigma, and then it's the positroid cell indexed by G sigma, which forevermore I'm just going to call C sigma, right? So indexed by sigma somehow. Okay, well, to think about this, I'm a concrete person, so I would like to actually choose a representative matrix for the points in this cell and think about what happens under the z tilde map. So, okay, so I told you how to get the Plücker coordinates for points in this cell from this graph, and then you have to think a little bit harder maybe about the representative matrix. But not that hard in this situation. Okay, so I'll tell you what the representative matrix is, and then we'll think about why it is a representative matrix. Okay, so for each triangle, black triangle in my subdivision, right, I have my little tripod in my graph. And maybe the vertices of this triangle are A, B, and C. Okay, the representative matrix, I should write it down in terms of the edge weights of this graph. So let me give the edge weights names. So this one is alpha I, This one is beta I, and this one is gamma I. Okay, in my representative matrix, if I look at row I, what I see is in column A, for this vertex, I see alpha I, the edge weight alpha I. In column B, I see the edge weight beta I. And in column C, oh sorry, plus or minus beta I. And in column C, I see edge weight gamma I. And all of the other entries of row I are 0. Okay, so why is this a representative matrix for the cell indexed by this graph? Well, we check if it has the right Plücker coordinates. So are its Plücker coordinates, do I get the generating function of perfect matchings on this graph? Okay, and if you think about it hard, you do. So what's the best way to say this? So okay, maybe I'll be a bit hand wavy. So this matrix that I've written down, it has one row for each white vertex, right? I've got a white vertex for each triangle and also one row for each triangle. So I've got one row for each white vertex, and I've got one column for each black vertex. And what a matching on my graph corresponds to, well, okay, sorry. So when I take the determinant, when I take a Plücker coordinate, I'm going to pick some columns, right? I'm going to pick k columns. And then when I take that determinant, I'm picking out some non-zero entries, right? If I do like let me take a step back. Okay, so what I want to say is that this matrix is some kind of adjacency matrix for the graph. Okay, and so when you take determinants of square submatrices, you only get a non-zero term when you select exactly the entries corresponding to a matching. So if you look at your determinant, all n factorial terms, many of them will be 0, and they'll be 0 exactly when there isn't a matching using those edges of your graph. Okay, so thinking a little bit, this matrix really does have maximal minors, kind of given by these generating functions for almost perfect matching. So okay, we're happy. It's a representative. Okay, cool. Oh, so we have a representative matrix. Now we can hit it with the z tilde map. But let's actually hit it with this z double tilde map, okay, and see what happens. Okay, so we've got this matrix, and we hit it with the z double tilde map. Let's call it y. And I'm trying to show that, well, z double tilde is injective. So from y, I want to recover these entries, basically, of my matrix. Okay, well, we said, what does this mean? Z double tilde A is equal to y if and only if A and y are perpendicular. So in particular, if I take this matrix, this row of this matrix, and dot it with y, I get 0. Okay, so let me, I think I need the columns of y here. Sorry, so I've got columns y1, yn. So in particular, if I take this matrix and I just multiply it by this row, I should get 0. So I get alpha I ya plus beta I yb plus or minus gamma I yc is equal to 0. Okay, so now we remember, where does this matrix live? So where does z double tilde take us? It takes us into grmn, which is gr2n here. So each of these columns of y, each of the columns of y is just a vector in R squared, okay? So I have 3 vectors in R squared, and they satisfy a linear relation. The linear relation is exactly that alpha I times the first one plus beta I times the second one, gamma I times the third equals 0. Okay. you can check none of these vectors are parallel. Okay, so you have 3 generic vectors in R squared. They satisfy some linear relation. There's actually only one linear relation that they can satisfy up to scaling. Okay, I think I'll write it over here. Okay, so yeah, so if you just have 3 generic vectors in R squared, they satisfy a unique linear relation up to scaling. And what is that linear relation? Well, if I take the Plücker coordinate, you can write it in Plücker coordinates like this. So PBC of y times YA plus minus PAC YB plus PAB of YC equals 0. Okay, so on the one hand, we knew that these vectors, YA, YB, YC, satisfied this linear relation. We also know that 3 generic vectors in R2 satisfy a unique linear relation up to scaling, which is that one. So that must mean up to scaling, alpha I, beta I, and gamma I are exactly just those particular Plücker coordinates of y. And okay, so that's it, right? So I have figured out what are these entries of the matrix A in terms of the matrix Y. And you can see injectivity from there. So Y is uniquely determining the matrix A. Okay, so this implies up to common rescaling, alpha I is just PBC, whatever the appropriate sign version of beta I, this is minus PAC, and gamma I is, okay. So if I wanted to, once I know y, I can just write down exactly what A is by putting in certain Plücker coordinates of y into these entries. That's how I recover A. So I'll take a step here. Maybe that was a bit confusing. Any questions? Mm-hmm. Mm-hmm. That's right, this matrix, yes. Mm-hmm. That's right. Talk about it tomorrow. Mm-hmm. That's right. Yeah. So that's tomorrow. Yeah. Yeah. So yeah, that's foreshadowing. So this is going to be generalized, which is one reason why I took the pains to tell you about it right now. So that's right. That is a really good question. So the choice of the triangulation of the black polygons here, they'll change your graph, but those different graphs will all be related by these moves. And the moves don't change the cell, they just change the parametrization you're looking at. So if I change the triangulation, I'll get a slightly different representative matrix, but the row spans will be the same. Yeah. So A here is a K by N matrix. So this is N, and this is K. K was also the number of black triangles that I started out with. It's also the same as the number of white vertices in my graph. Each row corresponds to one triangle or one hollow vertex. That's right. So this is, I've numbered my hollow vertices in some way. This is hollow vertex I. Oh. Yes. Yeah, so I guess, right, so I've written it in a way that hides z, but you'll remember, like, okay, at the risk of being confusing, this is the same thing as one of these twister coordinates of the matrix of x, where x is the z tilde image. And the definition of twister coordinate does depend on z, so z is hiding in there somehow. But yeah, the ability to invert this map does not depend on z at all. I think we expect that to be true, that in general, if the z tilde map is invertible, you can kind of hide the dependence, or sorry, what do I want to say? If the image of a positroid cell is a tile or not, we think it should be z independent, and the reason is some argument like this basically should work. But we don't know. Yeah, I think I'm willing to conjecture that. I think there was another question. Yeah. Yes, that's right. So I'm being a bit coy about the signs. We do write it down carefully in the paper. But yeah, so there's a specific, like you can always make, yeah, you can always make this sign plus, and then these two will be forced. And then as long as your parameters alpha I, beta I, and gamma I are positive, the whole matrix will be totally non-negative. Cool. So, okay, what I told you was, why is the z tilde map injective on these cells? Okay, so definitely like these do index tiles because the z tilde map is injective and the dimension is right. I'll just tell you the dimension is right. You might ask, why are there no other tiles? It turns out it's really easy. On every other cell of the correct dimension, the image just has lower dimension. It's not hard to show this. So these are sort of the only possible candidates for tiles, and you can show that they are tiles. Okay, now this. Okay, I want to say one more thing. Okay, about these tiles. Okay, so someone just asked, the only constraint I'm putting on alpha I, beta I, gamma I is that they should be non-negative. And as long as that's true, then this thing will be totally non-negative. So what that means is if I'm in this tile, like alpha I, beta I, gamma I, these are they're just some Pluker coordinates of y, or equivalently some twister coordinates of x. So to be in this tile, your twister coordinates have to have a specific sign. They have to have the right sign to make alpha, beta, and gamma positive. So kind of using this formula for the alpha, beta, and gamma in terms of Pluker coordinates, you can obtain a semi-algebraic description of the tile, which is the next thing that I'll write down. Wet. Yeah, it's not that hard to see this description, but maybe I'll just tell you what it is without trying to explain too much, because I want to talk about tilings. This. Okay. Okay, so I have one of these tiles. I'm just indexing them by this bicolored subdivision now. And I want to tell you, like, okay, forget about this thing upstairs, like what cell they came from. I just want to know, how do I describe this tile inside of GRK plus 2? Semi-algebraic description in its ambient space. Okay, so this tile consists of all of the points satisfying the following. So for all arcs in my polygon, I to j, that don't cross an arc of sigma, the subdivision, the twister coordinate, ij, is going to have a particular fixed sign. And what is this particular fixed sign going to be? Well, it's going to be the area in my subdivision IC to the left of the arc I to j. Okay, so let me maybe just do it by example. Over here. So here's an arc, 1 to 5, that does not cross the arcs of my subdivision. To the left of the arc 1 to 5, I see 2 black triangles, this one and this one. So the area to the left is 2. Okay, so, so maybe I'll write down. So this is the number of black triangles to the left of the arc I to j. And in that example over there, we were looking at the arc 1, 5, so that tells me about the sign of the twistor coordinate 1, 5. And we saw the exponent, it should be -1 to the 2, because there are 2 black triangles. And if I take all of the arcs that don't cross any arc of sigma, and I impose these sign conditions, that exactly cuts out my tile downstairs. And in fact, this is over constrained. So you can take a smaller collection of arcs, but I won't talk about it. So this is supposed to convince you, like m equals 2, also really nice, actually. So we can completely characterize the tiles. We have a nice recipe to come up with these playback graphs. If you hate playback graphs, we also have a nice recipe to just describe what these tiles are. And you'll see, kind of surprisingly, okay, so the tiles, they're sitting inside of GRKK plus 2, which is curvy. Like there are some non-trivial Pluker relations here. But the tiles are just, you take some linear subset of the ambient projective space and you intersect it with your curvy Grossmanian. And that's what the tiles are. Oh, I'm sorry, there should be a circ here. So it's not too bad. Like, it's as close to a linear slice as you can get, given that your ambient space GRKK plus 2 is not linear. Okay, and this is behavior that stops at m equals 2. So this is a small m phenomenon. It's not something that's going to carry forward.
This is the tile downstairs.
This is the tile downstairs. That's right, that's right. Cool. Any other questions? I'll talk about tilings very briefly. Yeah, it's oh gosh, it's a refinement of the Schroeder numbers. We have it in our paper. Yeah, okay, I don't know if there's a closed formula, but they're in bijection with what are called separable permutations with exactly k descents. So yeah, yeah, you're just counting these objects, right? And there's some number of bicolored subdivisions of an n-gon, and then you refine by the area. And this, I think the bicolored subdivisions, that's a Schroeder number, and then the refinement is by computing the area. Yeah, we're just, yeah, exactly. For m equals 1, these finest tiles, you're just, yeah, you're doing like a stars and bars. Yeah. Any other questions? All right, now for tilings. So this is a very weird result, which I'm quite fond of, but don't really understand. I mean, we proved it, so it's definitely true, but I don't really know why it's true. So I'm going to define for you something that seems totally out of left field, and then I'll write down a theorem, and we'll both go, huh, okay. So let me define the totally out of left field thing. Okay, so I'm still using these bicolored subdivisions. Okay, and I'm going to define for you a polytope in Rn using this subdivision. So this is going to give me a polytope P sigma. And this is going to consist of those points in Rn where, okay, the coordinate sum needs to equal k plus 1, and I have an inequality for each one of these arcs, okay? I'm just going to write for all arcs I to j from previous theorem. I have an inequality which bounds the coordinate sum from xi up to xj minus 1. And the bounds are going to be, this coordinate sum has to be bigger than the area from I to j, and it has to be smaller than the area from I to j plus 1. Okay, so who knows? I pulled these inequalities out of nowhere, but for sure they define, well, at least a polyhedron, and I promise you it's a polytope. It's bounded. Okay? All of these polytopes are matroid polytopes. They live inside of the hypersimplex, which let me tell you what that is. So P sigma sits inside of the hypersimplex delta k plus 1n. So this is the convex hull in Rn of all of the 0, 1 vectors with exactly k plus 1 ones. Okay, so this is convex hull of 0, 1 vectors in Rn with k plus 1 ones. Okay, and these polytopes P sigma that I pulled out of nowhere, their vertices are all vertices of the hypersimplex. So they also have 0, 1 vertices. Okay. Well, okay, let me draw you just the only picture that I can draw of this situation. So this is the hypersimplex delta 2, 4. So vertices are indexed by these 0, 1 vectors with exactly 2 ones. So like here's 1, 1, 0, and maybe here's 1, 0, 1, 0, and you fill in the rest. These polytopes P sigma, one example of a P sigma is this like top pyramid. That's one of these P sigmas. And another one is the bottom pyramid. Okay, here's the theorem. So if you have some collection of tiles for the amplituhedron that give a tiling. Oh, sorry, let me write it this way. So and K2Z. So some collection of tiles for the amplituhedron is a tiling for all matrices Z if and only if the sort of corresponding polytopes P sigma give what I'll call a tiling of the hypersimplex. Okay, and what does a tiling mean? Well, I'm just going to declare my tiles are going to be these P sigmas, and so a tiling is a decomposition of the hypersimplex into these P sigmas so that the interiors don't overlap. All right, so all that this means is a tiling means that the interiors don't overlap, and the union covers the whole thing. Okay, so this is the theorem. So we had the amplituhedron, m equals to amplituhedron. I pulled out of nowhere some seemingly unrelated polytopes, and the decompositions of the amplituhedron into tiles somehow combinatorially exactly the same problem as decomposing the hypersimplex into these polytopes. Yeah, go ahead. Yeah, so one wants this. This is 2k dimensional. This is n-1 dimensional. Sometimes 2k is bigger than n-1. Sometimes it's smaller than n-1. So in general, you can't hope for like a surjective map all the time or an injective map all the time. Actually, we don't really understand geometrically why this relationship is true at all, except what we can say is like the facets, okay, these polytopes have some facets. Some of them are on the boundary of the hypersimplex, some of them are not. The facets of P sigma that are inside of the hypersimplex are in bijection with the facets of this tile that live on the inside of the amplituhedron. So you can think about this kind of statement as saying, okay, what do you want if you have a tiling? Well, you start with a tile, and then anytime you pass through a facet, you should land in another tile, and kind of like not before. And so since the facet structure is very similar between these two things, that's sort of one reason why the problems are the same problem. So that's kind of, that's as much of a geometric understanding as we have. Yes. Yeah, I'm saying, oh, I don't know. Is it, if I think about like matroidal subdivisions of the hypersimplex, is there? I guess so. I mean, yes, all of these are like series parallel matroids. Yeah, so I don't know. Maybe it is always a tree. I'm not sure. Mm-hmm. Yeah. Mm-hmm. So yes, in fact, well, that tree is another Playbit graph, and that tells you which positroid polytope this is. But that tells you about one polytope there, not like the structure of the entire subdivision. Yeah, maybe I'll say one thing, which is, maybe I'll just draw one commutative diagram and say this is the other way we understand this geometrically, which is basically still not at all. So we've got the totally non-negative Grassmannian with the Z tilde map goes into the amplituhedron. And we also have a totally non-negative Grassmannian for K1 bigger. And you can use the moment map. You can hit this with the moment map and obtain the hypersimplex, delta K plus 1n. And so what we're asking for is somehow how to fill in the arrows in this diagram. And we know how to do it combinatorially. There's this map called T-duality or T-shift, which takes us from here to here, but only at the level of the combinatorics. And so the question is, yeah, like what geometric maps go there? And I have no idea. That was mostly to Lizzie, I guess. Any other questions? Yeah. Yeah, that is such a good question. Like we have a good combinatorial model for the tiles. Surely we can say which ones fit together. No, we don't. We do know that, like we know some properties. So if you have a collection of these bicolored subdivisions, if they form a tiling, then when you stack them all on top of each other, you should get a like n-2 choose k covering of the polygon. Like the black stuff should cover every point n-2 choose k times. But I think it's not a sufficient condition. But yeah, I think that's basically as far as we have. Yeah, it's a really good question. We thought about it for a while, but didn't see